This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So good morning, welcome to lecture number 22 of the International Winter School. Today we'll turn to a discussion of black holes, and in particular the Schwarzschild black hole. Now, if you couldn't be here for the last 6 lectures, that's not a problem, because what we do today only depends on lectures 1 to 15. There's a fresh start, if you wish, and the same will be true on Wednesday, when there will be again a fresh start. So now the topics stop being dependent totally on everything that happened before, so maybe that gives you some comfort in studying this. Now, what we wish to do here in this lecture is to study the Schwarzschild solution. And you saw the Schwarzschild solution, and in fact you verified that the Schwarzschild solution is a vacuum solution of Einstein's equations. You saw this in tutorials, right? And what you checked there is that if you plug in the following metric, G, being a 0-2 tensor, can be written as 1 minus 2m over r, where this little m is short for capital G, capital M, where this is called the mass of the Schwarzschild spacetime, and G is Newton's gravitational constant. You can write it like this: dt tensor dt, or in other words, in coordinates where t is one coordinate, it's the first entry of the matrix for the t in those coordinates, minus 1 over 1 minus 2m over r dr tensor dr, minus r squared d theta tensor d theta, plus sine squared theta d phi tensor d phi. Or again, as I said, in other words, it's a diagonal metric in coordinates t, r, theta, phi, where the diagonal entries are this factor, this one, minus r squared and minus r squared sine squared theta. You check that this is a vacuum solution in a chart in the so-called Schwarzschild coordinates. So the metric is called the Schwarzschild metric, and that refers to the G, but the coordinates in which this is formulated are, maybe unfortunately, also called Schwarzschild coordinates. Of course, you could express the Schwarzschild metric in non-Schwarzschild coordinates, but here the Schwarzschild metric is expressed in Schwarzschild coordinates, and those are coordinates t, r, theta, and phi. And the t can take values from minus infinity to infinity, r can take values from 0 to infinity, theta from 0 to pi, and phi from 0 to 2 pi. Now, we will be careful to keep track of the ranges of variables here, because you remember that in the beginning we studied quite a lot manifolds and chart transitions. And we emphasized very much that one chart may not be enough to cover the whole manifold. And we also discussed that if you know something in a chart, outside this chart domain, there may lie still parts of the real world you haven't seen. Now here, with the Schwarzschild metric and Schwarzschild coordinates, you can draw pictures of that, and we'll do that. And you can live happily under the illusion that this covers the entire world. And then you say, yeah, maybe here there are lines taken out because of the breakdown of these polar coordinates, so to speak. But other than that, this certainly covers the whole world. Well, today we'll find out that this is far from the truth. And we'll find out that understanding this metric is only possible, really, if we find other charts that extend this chart quite a bit. So what seems to be a complete world, in fact, is not. So the remark I wish to make is the following. when staring at this line element, or when staring at this metric for a while. Well, that's an important theoretical technique, to stare. When staring at this metric for a while, two questions naturally pose themselves. The first question is, what exactly happens at r equals 2m? And so if I ask this, you say, why am I interested in r equals 2m? Well, at r equals 2m, 1 minus 1 is 0, and worse, 1 divided by 0 is infinity. Aha! Why didn't you complain when I said r runs from 0 to infinity? It doesn't. It doesn't. In these coordinates, r may run from 0 to 2m exclusively, and then this may then run again from 2m to plus infinity. It's this union, this disjoint union, and the 2m, r equals 2m, cannot be assumed for this metric, because even if you ignore this, the metric becomes degenerate here. So one component is 0, the other one is infinity. What a mess. Okay, so first insight, this r, which we might have thought as a cozy radial parameter, cannot take this value. Yes?
Well, we impose a lower bound of 0 on r.
Pardon me?
For the degeneracy, because you could admit negative numbers as well, no?
Yes, but the point is that is now, well, we'll see. So the point is, we'll start here and we'll see whether this is all you have. So if you suspect that there might be something beyond the 0 to 0 or minus infinity, we'll discover it. Why does nobody ask whether there's something beyond minus infinity and something beyond infinity here? That's the second question. Second, is there anything in the real world beyond t minus infinity and t plus infinity? And that may sound like a very silly question, but in fact it isn't. Because you say, well, what could be beyond infinity? Don't be ridiculous. Remember, this is just a chart. So the idea is the following. It's just a question, right? We'll see. The idea is the following. If I have a map of Linz, and it covers the entire area of Linz. Let's assume Linz is rectangular. Linz. But then if you go beyond that, you come to the next town, okay? Why wouldn't I take this chart, if this is already a chart, and I would blow it up to a chart that's infinitely large? That's the whole plane. I can do that, right? I can take this interval from 0 to 1, say, or minus 1 to 1, and I can blow it up in a one-to-one continuous manner to the whole real line. Then Linz would be, you would come to the boundary of Linz if you go to infinity on the chart, or to minus infinity. Does that imply that beyond that infinity in that chart there is nothing more to the real world than Linz? Of course not. This could be the case here. So it's not a silly question. So that's the point. You work with charts and you need to understand what a chart means. So if you understand what a chart means, and we do understand that, then you come up with all kinds of questions and all kinds of problems you didn't have before, and that's called progress. So the point is, how do we get insight into these questions? Because obviously if we look at it from this point of view, we won't, because these coordinates themselves then are the problem. How do I transcend the coordinates by using them? So insight into these issues, into these two, and of course the same point could be made for r greater than infinity or something like this, right? So insight into these two issues is afforded by stopping to stare. Right? That's also a technique. So you stare and then you stop to stare, because what is the insight? The insight is, if we want to learn something about the real world, we should look at objective objects. Not at chart-dependent objects, but at objective objects. What is objective if you have a metric? Well, what is objective is, for instance, what are the geodesics of the metric? They might then be expressed in those coordinates, but as objects as such, they describe something in the real world. Okay? Look at geodesics of G instead, because that's something in the real world. That's how we transcend the coordinates. Although we still work in the coordinates, we look at an object that's not coordinate dependent. Okay, so what we do, first section, is we look at radial null geodesics. Now this is just terminology. A null geodesic is a geodesic whose tangent vector at every point is 0. That's a null geodesic. It's the world line of a massless particle. So let's consider these in Schwarzschild. Consider null geodesic in SCHD. That's the short form for Schwarzschild. Okay, let's consider null geodesic there. So what do you need to do? Well, you need to look at an action for this massless particle. And how do you get this? Well, you have this. Now you have the G v gamma of lambda. And in Schwarzschild, this becomes 1 minus 2m over r t dot squared minus 1 minus 2m over r inverse r dot squared minus r squared theta dot squared plus sine squared theta phi dot squared. That is the action for a massless geodesic if you provide the information that it's a null geodesic with the expression in brackets being 0. That's the additional condition. Now you say, oh, if I plug this in, it's 0. Well, you mustn't plug it in at this point. At this point, you first need to vary, and then you plug in. And one has, in particular, the R equation of motion. You know you have an action, you vary. You can vary with respect to various variables. And the one we are interested in is the, no, actually we're interested in the T equation of motion. Why did I always write R? Yes, we're interested in the T equation of motion. In principle, we're interested in all, but we'll see the T1 suffices. What's the T equation of motion? Well, it's the Lagrangian by T dot. That gives you a 2 times this. Then the result derived minus the Lagrangian divided by T, derived with respect to T, but there's no T in here, so the T equation of motion is actually 1 minus 2m over r, a factor of 2 I don't need, T dot, the whole thing dotted equals 0, right? That's the T equation of motion that follows from there. I would be crazy if I evaluated this dot on here and on here, because I know the result is 0, so I can eliminate the dot and immediately have one integral of motion. I know this is some constant k. Okay? So it's my T equation of motion. And I have this null condition. And with these two alone, so I can get extra equations of motion from here, but I will not need them, because what I will look at is only consider radial null geodesics, which means in addition to these two conditions, I already provide that theta ought to be constant and phi ought to be constant, which defines radial. I'm talking about a particle that falls in radially without any theta or phi component changing. So these are the radial null geodesics, and that is then the integration of the other two, which I here do by assumption because I look at a particular case. Now, if I have this null condition, which means that the square bracket is 0, and I use the equation of motion here, I can do the following. I can obtain from the first box and the second box, it actually follows that r dot is plus or minus k. How do you see this? Well, you solve this one for t dot, that's k divided by the round bracket. You plug it in, that gives you a k squared divided by the round bracket squared, so it gives you a k squared, I'm sorry, so this is, yes, so let's first do this, is a k squared divided by the round bracket minus, you have an r dot squared divided by the round bracket, you multiply by the round bracket, you get this one, and this is of course the case if and only if r dot is plus minus k. Okay, this is just insertion. Yeah, you say, interesting, but what do I learn from this? Well, you learn a great deal. The dot here is this parameter lambda, and we had an affine parameterization. Therefore, you can solve this. You can solve this. You have two possible solutions. You learn that r of lambda is either plus or minus k times lambda, right? What does that mean? It means that if you just see k times lambda, and lambda is an affine parameter that parameterizes your world line, you see, oh, constant times that is still an affine parameter. So you learn that the radial coordinate can serve as a different parameterization for your world line without changing that it's affinely parameterized. Aha! Hence, we may consider, instead of solving for t of lambda, we could solve for some t twiddle of r, which is the t of plus or minus k lambda. If I write plus minus, we have to make a case distinction. Okay? So normally I would solve these equations of motion for t of lambda, r of lambda, theta of lambda, phi of lambda, and then I have a parameterization of the curve in the space-time, right? But now, because of the special situation, I see instead of parameterizing by a parameter, which I could choose arbitrarily, I choose the r. I can choose the r as an affine reparameterization, and I can express directly the t in terms of r. Okay, so I get rid of the parameterization. That's kind of useful, as we will see in a second. So how does that work? So let's do case A. Case A is of this plus minus, I choose the plus. And then next second we'll choose the minus. So if I look at this case, I can calculate what's dt twiddle by dr. So in physics it's often custom to just write, instead of t of lambda, one writes t of r. But of course, the t twiddle depends on r differently than the t depends on the lambda. So it's better to write it like this. dt twiddle by dr. What is this? Well, you can think of the chain rule. You can say you first derive this t twiddle with respect to dot, and then you derive the r with respect to dot. Okay? If you do that, then of course you get a chain rule. You get a, in this case, plus k divided by, now you look at the r, so the t twiddle dot is this one times the t, hang on a second, times the t, it's the t dot times the k, but the t dot we had is k divided by this guy. Okay, I'm sorry. Okay, so this is k divided by this guy is 1 minus 2m over r, and then from the r dot you get the k. So what you get here in total, if you expand by r, is r by r minus 2m. Is that right? Yes, that's right. Okay, so anyway, we know how this one increases there, and this can be integrated. So you know the derivative of t twiddle. So you learn that t twiddle of r equals r plus 2m ln r minus 2m. That's the integral. As you very quickly see by deriving this with respect to r, you get 1 plus 2m divided by r minus 2m. If you bring this to the same denominator, you get back to this guy. Okay, so this is quickly solved, and that's it. We found the null geodesics. Well, that's case A. Let's quickly look at case B. Case B is if we choose the minus sign here, and we follow a similar route, and we get to t twiddle of r, so maybe we call this t plus and this t minus. T twiddle of r is then minus r minus 2m ln r minus 2m. And I calculate, yes, so we have the derivative here. So these guys here you can check by looking at the sign of this. These guys up there are the outgoing null geodesics. See in a second why we call them outgoing. And these are the ingoing or infalling, ingoing null geodesics. Well, let's draw this picture. So we start with the Schwarzschild coordinates t and a Schwarzschild coordinate r. There's the special point 2m, and I just have some line here to know where 2m is, but this is just in my, I'm sorry. So this is just in my mind, this 2m. And now I start drawing these null geodesics. Now let's look first at the ingoing or the outgoing ones. So the t, that's this t here, of course the other t is just with a different parameter. This t here is this function of r. So what happens if I come from the right and I approach 2m? If I approach 2m, the ln goes to minus infinity, right? Goes to minus infinity. So then to minus infinity, I add r. I'm not very impressed, but the point is these outgoing null geodesics, they are like this. So I should use different colors. Okay, so the outgoing null geodesics, let's start with them. I start doing them in this region here. They look like this. They all go asymptotically to here, and they go somehow like this. Okay, that's what they do. They go on like this. That is for r greater than 2m. For r equals 0, I must not even look at it because r equals 0 is not part of the chart. Now there is a second region where I can look at these guys, at the outgoing ones, and it's the same story. It's just that the r is smaller, so there they run like this. It's always drawing this funny ln function there, okay? So these are the outgoing ones. The green in this outer region and the blue ones in this inner region. That's just the geodesics in Schwarzschild coordinates. So that's the map of Linz. In Linz there are light rays running. Okay, I mean, you know, Linz is not a space-time piece, but a space piece, but something like this. So this is an objective picture in those coordinates. But these guys mean something. This is what light does, expressed in these coordinates. So now we need to look at the ingoing null geodesics, and how do they look like? So there is this minus there, so this is actually minus this up here, so I can everywhere take the outgoing ones, as they're called, and I flip them and I get the ingoing ones. So let's do it for this one here first. So I need to, what do I have down here? I need to reproduce here, something like this. That's too steep here. Chop. and then I go here like this. Well, so here asymptotically, and then I go away. Here the same thing, I reproduce this, go asymptotically away, not asymptotically, I go away, and here I approach asymptotically this here. And then finally this one, and I asymptotically go here. Oh yeah, that's doesn't look very good, but it's true. I mean, you know, it's an art to draw, but those are these. And then we have in the inner region, we have a similar situation. Like this. This one goes like that, asymptotically here. And finally, which one don't I have? I don't have this one, so this one goes like so. Okay, so maybe that's a little confusing, so let's be careful. So the outgoing ones, so these guys would kind of run in this direction. And so here the ingoing ones are yellow and red. Okay? So the yellow ones are ingoing ones, so they run in this direction. And before I go to the inner region, let's observe that these are null geodesics. So at every point they're tangent to the cone, which means that if I draw the cone like this because I suppress the other directions in the diagram anyway, that there must be a light cone there like this. There the light cone must look, I mean a light cone at this point, you know, it lives in the tangent space, so I can only draw it locally. So roughly speaking, in the tangent space at this point, I have this light cone, there I have this one, there I have this one. You can construct from this, you can see in the Schwarzschild coordinates what the cones look like. Okay? So in the Schwarzschild coordinates, cones out here rather look like this. Okay? But the further you go in, the more they're squeezed. But you observe, although they're squeezed, they refuse to tilt or something. They always stand upright like this. Okay? Okay, so let's look at the geodesics inside. So the infalling ones, these guys actually run in this direction, and the blue ones, they are the outgoing ones in this inside direction. They run like, hang on a second, they're the ingoing ones. No, it's right, I think. This one runs like, hang on a second, they run up here, down here. Yeah, they write, hang on. Are they upside down? Okay. Not entirely sure that's true. Yes, that's right. You have to orient, but nevertheless here, I thought they stand like this. I'm now a little bit puzzled here. Let me think for 1 second, please. So don't go out, in, out, in. I also think it should be like this now, okay? Okay, but that doesn't hurt us, okay, however they stand, okay? So we have a situation like this, and yeah, that's it. Those are the geodesics of Schwarzschild, and now you look at this and you say, haven't I read in the popular literature that Schwarzschild is a black hole, that at 2m there's an event horizon where light can only go in massive matter, but it can't come out? Well, it doesn't look it can go in, right? Because any null geodesic approaches this 2m, approaches it, and however far you go, you will not cross it. So light does not fall in. Maybe we overlooked something. Now think again of the question about Linz. So assume Linz is a space-time region rather than just a space region. As long as I'm in this chart, which extends to t to infinity, I do not cross. Well, but maybe this chart only covers everything up to the boundary of Linz. Then the chart is at infinity, but that doesn't mean that beyond Linz there's no more to the real world. So it's true, I mean what we calculate of course is true, within the Schwarzschild chart, an outer infalling null geodesic, radially infalling null geodesic, will not cross the horizon. Yes? Yes? Yeah, I think this one must be oriented like this. They must be like that, right? They are like this. Okay, let's, yes, now I know why I'm, okay, let's, let's not spoil the moment. It's not a crucial point right now. Okay, it's right. I also think that they are like this. Okay, but let's look at this. What happens here? So the yellow and the red ones are the infalling ones, right? That we got from the infalling solution, from the ingoing solution. Now, isn't it already a little bit suspicious that the infalling ones, they run up to infinity here in this chart, say to the city boundary of Linz, and then assume you had a map of Linz, and you see that there's somebody who lives here and he commutes to work every day up to infinity, right, because I stretch this to infinity, and then in the evening he goes and visits his parents, right? So the point is that people, I mean I shouldn't say it's the same one, but people are kind of running here every day, and you have also people running here. Well, you might suspect that there's something beyond Linz, and that beyond Linz they actually return. You see what I mean? Even if your chart doesn't show that, right? That's in fact the case here, but we need to find out whether it's really the case. You run here with the yellow ones and you come in with these ones. The point is beyond the chart, really the particles cross the horizon. Now how do we see this? It's just a suspicion from our thinking about charts that could be the case. The question is it the case? Question? No. Okay. So so the question, and I should have, of course, before I wrote the integral is this and that, I should have written plus constant, because that makes the different ones, right? When I integrate plus constant. Okay, sorry. Okay. So the idea, to follow this idea, is to introduce the Eddington-Finkelstein coordinates. Question? You keep knocking without asking. Okay, good. Eddington-Finkelstein is a new chart, and in order to figure out what's really going on, there is a brilliantly simple idea. Brilliantly simple idea. Change on the domain of the Schwarzschild coordinates. Nowhere else, how would you? Change on the domain of the Schwarzschild coordinates to different coordinates such that in those new coordinates ingoing null geodesics, only the ingoing ones, ingoing null geodesics, because we're interested in their fate, appear as straight lines of slope -1. Aha, can this be done? Well, of course it can be done. This is achieved by the new coordinate t bar, which of course can be expressed as a function of the old coordinates. and if you wish, this is the chart transition map. It's given as t, the old t, plus 2m ln r minus 2m. So remember before, the null geodesic had, so recall that the ingoing null geodesic was given by t twiddle of r, that's now just a function, equals, that describes the null geodesic, equals minus r plus 2m ln r minus 2m. So here we had an r, but here we now have a t. But the point is we want that this here, in the new t bar coordinates, in fact is a straight line. Well, this is easily seen because this was the t from there before. So you have t plus 2m ln. No, wrong. You have to solve for this t and plug it here. So you have t bar minus 2m ln r minus 2m equals, so this is the null geodesic in Schwarzschild coordinates. And now we reformulate this same equation in the other coordinates by replacing the t by this minus this one equals minus r minus 2m ln r minus 2m. And here I forgot plus constant. Now I have it here, plus constant. And you see this one goes against this one. That means in the new coordinates, the equation is given by minus r plus constant, which is precisely what we wanted. We wanted a new t coordinate such that the null geodesic appears under this slope. So let's draw a picture. Yes, you can. Let's draw a picture. So this is now the new t bar coordinate. We have the r, we have the 2m, but now you need to tell me the infalling outer ones had what color? The infalling outer ones had the color? Or you used probably different colors. Pardon me? Nobody remembers? No, I think it was either blue or green. The out here, incoming yellow. These were yellow? Okay, good. So these are now slope 1, slope 1. Here there's nothing because I didn't have that. But in both regions, the transformation yields this for an infalling null geodesic. Plus constant. It's the next infalling null geodesic. They're all straight lines, as you can see. And yet another one, infalling null geodesic. They're all parallel lines of slope minus 1. Okay? That's what they are. Aha. What is it with the outgoing null geodesics? Okay. What is it with the outgoing null geodesics? I got them like this, but with a plus sign here. But if I do this, I still replace the left-hand side by this, take it to the other side, but now there was already a plus here and there, so the outgoing ones have t bar equals minus, no, not minus r, equals plus r, because there's an overall plus here, plus r, and then plus 4m ln r minus 2m plus constant. Aha, so the 2 changes to a 4, but it doesn't look nicer. So it is not the case that by this transformation we also got the outgoing ones in a nice fashion. By the way, so I should have probably drawn these inner ones here by the orange line, because I had different colors. I had different colors before for the ones inside and outside, right? Remember? So it's like this. And these ones here, whatever color they had, blue or green, was blue outside. Anyway, they're still like this, but they become, the singularity here becomes multiplied by 2. Okay, so qualitatively, it still looks like this. Okay, these are still the outgoing ones here, and inside it still looks like this. Stuff like that, okay. Now let's draw in this chart the cones again. Well, the cones, so the outgoing ones somehow like this, and the ones in here in green and blue. So these guys go like this, and these here go like that. And so the cones are like so. Okay, and let's draw the cones out here. We have a cone here. Again, I mean, I add this little circle that doesn't really belong to the two-dimensional picture, but then you have the right idea where the little cones sit. But now you see, well, something is, no, it's, all is fine, because you can now draw the one that runs here really, close, 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 and only up here goes away. Okay, and here you have this cone, and there you have this cone. Okay, and here, this is an interesting point. You have this cone, and you see the closer now you go to the horizon, if the horizon was there, but it isn't, right? It's not a part of our original Schwarzschild coordinates. If the horizon was there, they would all conspire to stand there like this, the cones. Do you see that? Aha. Okay, so that's the case. Now the question is, what has happened? Well, what happened is we made an innocent coordinate transformation inspired by the idea that I want to see how somebody comes to this. In the previous picture, the ingoing null geodesics also approach the horizon, but I now choose coordinates such that they approach the horizon in a straight line, which is just a coordinate thing. But then the one, so in the previous chart they went up here and these came from down here, and what I do by this coordinate transformation, I go to a T, and then the closer I go to the horizon, the more I pull a point from plus infinity down. Because if I'm on the horizon, a point that was previous TR is now the point T plus this R, and this for R to 2m becomes minus infinity. So the point is, I took the previous diagram and go to the horizon, and at the horizon I pull down, and I pull points down from infinity. This point here was previously at infinity. This point that doesn't exist here was previously at infinity. This one was also at infinity. This one was also at infinity. All this little necklace of points that are here, I pulled them down from infinity by this coordinate transformation. And hence, what previously looked like up to infinity at this r equals 2m, and then back from infinity, I pulled that down in such a way, and not only here, I also pull it down here and here and here, but the further I go to the right, the less I pull. I pull the most, namely from up infinity down to a finite value here, at the point r equals 2m. A little bit right of that, I only pull a finite distance, okay? It's only here that I pull infinitely much. A little bit here I put finite, here even less finite, and so on, such that this line becomes straight, and I pulled up this point at infinity here. I pulled it to here, and then this guy Looks like this. That's funny, right? But that's exactly it. I went beyond the confines of the chart of Linz, which was a chart that was blown up to infinity, although it only covered, in quotation marks, a finite area in the real world. Okay, so that's this diagram. And now, of course, you say, what is the problem with this 2m bit? There is none. So I include these single points, which were not part of the Schwarzschild chart. So what I do is I say I now have a new chart. So consider the new chart v, y, while ux was the Schwarzschild coordinate chart. Okay? So the previous one we call ux, and now we have a new one, uv, and you know that the intersection, no, that v, if you take out u, that all that, or maybe better to write u union, just now the domain, union with the horizon here. So these points here, this line, this dashed line, I call the horizon, for reasons we're going to discuss in a second. And now this horizon, well, at least in the real world, it's the horizon. So it's the chart image of the horizon. So u together with the horizon, that's v. So Schwarzschild only covers this. And now we made the chart bigger, but in such a way that on the overlap, which is just u, on the overlap, it coincides. That's how we constructed it. Yes?
We restrict ourselves to only the ingoing, so outgoing null geodesics, because I mean, in this case, it does not make any sense for the outgoing geodesic to have them also in the chart, and vice versa. I have only the possibility to have a non-singularity for the ingoing or outgoing.
No, the point is you need both geodesics in order to span a coordinate system.
But how can I define the, in this case, outgoing? Because I mean, I have the singularity.
Well, they're outgoing null geodesics, but they're not future pointing. So you don't have particles run along them. So that's the old idea. If you're at a point and the G defines the double cone, and a curve, a vector standing inside here is as much time-like, or say null, this vector here is as much null as this vector is. They're both null. And hence, this is a null geodesic, and the same, this is a null geodesic. I didn't say I want to look at ingoing future pointing, outgoing part future pointings. Okay? Okay? So the distinction only comes when you have the time orientation. Okay, so, okay. Good. Okay. So, but indeed, there is in fact a coordinate chart that's, they're not called Eddington-Finkelstein, but Kruskal. There also the outgoing ones run at the same time at 45 degrees. I'll comment on that, but let's first continue here what we want to do. So now we change to new coordinates. The picture looks nice and convinces us, okay, there's something going on. We now see really these guys do cross this horizon without any problem. It was just an artifact of the previous chart, which pretended to be a very big chart, but it was just unduly blown up. So really beyond infinity, there was much to be pulled down. Okay, so that's this, but this is just the picture. The picture is very useful. We constructed the picture from formulae, but what we should really do, we should calculate the metric in the new coordinates. So now calculate the Schwarzschild metric G. You see the metric remains the metric. That's an abstract object in the real world. Now calculate the Schwarzschild metric G with respect to Eddington-Finkelstein coordinates. Eddington-Finkelstein coordinates. How does one do that? I mean, you know it in theory, but let's do this once in practice. So you have a new coordinate t bar that depends on the old coordinates, like t plus 2m ln r minus 2m. That's it. And you have a new r, which depends on the old coordinates, like the old r. You have a new theta that depends on the old coordinates, like the old theta. And you have a new phi that depends on the old coordinates, like the old phi. Informally speaking, we only change the t bar coordinate, but not so informally speaking. You have a new r coordinate, it just happens to be the old one. Okay? So you change set of coordinates from unbarred coordinates to barred coordinates. So and of course, in the terminology from before, I have y0 to y3 are the barred coordinates. Right? I just use this nomenclature because it's a little bit easier to remember. And the old x coordinates are called like this. Okay, so this is just different names, but I try to make connection to the general formalism. Okay? So what do you need to do if you want to know the new components? If you want to know the new components, G in the Y system, that's the new system, and you want to know the A-bth component, well, you better take the component Mn in the X system, and you do dxm by dxm by dya, dxn by dyb. Is that the right way around? Yes, it is. Okay, so this is the coordinate transformation, the transformation of components of a metric from the X system, the old one, into the new system. Schwarzschild coordinates, Eddington-Finkelstein coordinates, which we like better. Okay? So what do we need to do? Well, we need to calculate x by y. X by y are the old ones derived with respect to the new ones. Oh dear, then we have to invert this guy. Yeah, we can do this. Everything can be done. But let me show you a trick that always works. You always choose the direction that suits you better. In this case, I don't want to calculate x by y. I calculate y by x. And you learned and you checked in the tutorials that if you know this matrix, row column, that this is the inverse matrix. You remember? So we can calculate this one and then we invert the matrix. Let's do this once because here you may be able to invert and it's very quick, but let's do this once as a check. So how does this go? Well, you need to say what you mean. This is the row index and this is the column index. So for 1, 1 or for 0, 0, you derive the 0 with respect to 0. This one with respect to t, that's a clear 1, right? Then you continue in this row. So you stay with the 0. You derive this with respect to the r. What do you get? You get 2m divided by r minus 2m. Is that right? That's right. You derive the same one with respect to the theta is 0 and with respect to the phi is 0. You derive this one with respect to t, no t in it. With respect to r, yes. With respect to theta, with respect to phi. Derive this one with respect to t, to r, to theta gives a 1, to phi a 0. This one with respect to t, 0, r 0, theta 0, phi 1. That's the matrix. Okay? Comes in useful to practice this for exams and stuff. So you get this thing. Now what's the inverse of that matrix? dxb by, or dxa by dyb. This should be the inverse. Well, let's guess 1 minus 2m by r minus 2m. 1, 0, 1, 1, and the remaining ones all 0. Okay. Let's check where this is the inverse. So we come with this matrix from the left to this one. This times this gives a 1, row times column gives a 1. Okay, that's the 1. We want to get the identity. So we take this row times this column. This is 1 times this, minus 1 times the same is 0, 0, 0, and so on. You can check this is the inverse. Okay? Aha. So now we have this inverse. All that we need to do now is we need to evaluate component by component what the new components are. I think I'll do this in the middle so I can still peek at the other blackboard. So we're simply finding the components of the metric in the Eddington-Finkelstein coordinates according to the general rules we worked out. Thank you. So we start with G, Y, the 0, 0 component, which you could also call the T bar component. It doesn't matter. You know, we use this rather flexible notation, equals. Well, in order to get the 0, 0, what you need is you need the Y0 down here. Now here you have in the X system, the Mn, you have a dxm, dxn. Now we remember that this is the metric in Schwarzschild coordinates, the components of the metric in the Schwarzschild coordinates. You remember that was diagonal? So we only need to check for m equals n, 0, 0, 1, 1, 2, 2, 3, 3. And we always have to write this here. So let's do this. So we start for G0, 0 here. The G0, 0 is 1 minus 2m over r in Schwarzschild coordinates. You agree? That's the G0, 0 in the Schwarzschild coordinates. And we multiply by x0 by y0, x0 by y squared 0. So the thing squared, x0 by y0 is a 1 squared is a 1. 1 times. Now comes plus. Why plus? Well, it's a summation convention. There must be a plus. Now comes the 1, 1 component of Schwarzschild, but the 1, 1 component of Schwarzschild is minus 1 over 1 minus 2m over r. Remember, that's the signature that comes in here. So we could use this minus to make this to a minus. And then we multiply by x1 by y0, x1 by y0. x1 by y0 is minus this guy, is this guy squared. So it's minus 2m by 1 minus 2m over r. Is that right? No, by r minus 2m. By r minus 2m all squared. Plus summation convention comes the G33 times x3y0, x3y0 is 0. The same for x4y0, x4y0, also 0. So there's nothing more. Plus 0 is the full summation convention, yields 1 minus 2m over r minus 4m squared divided by r minus 2m squared times, and I expand this one by r 1 minus 2m. No. I write an r up here, which is 1 over r down there, r minus 2m, right? Yes, I divide by r and I get this up there. I'm confused. Pardon me?
It's a multiplication of r to the nominated denominator.
Confused. Is this right what's written here? Okay, it's right what's written here. So I just need to take this to the same, so but it is a third power here. I'm confused.
You can divide this term in square by 2m, both denominator and denominator.
I take it all out or what? So tell me what you write and we check whether it's true. You tell me. square. What did I write?
Okay, so there is 1 minus 2m over r minus 1 minus 1 over. Oh no.
Okay, so yes. Pardon me? You need to speak louder. I don't hear.
So we are calculating m equals 1 and down is 0. So first the row is 1 and the column is 0, which means it's wrong.
Ah, yes. So the second one is wrong. The first one was right, was the 0 by 0. The next one is 1 by 0. But 1, you see, it's important that you remember this is the row. I need to go here. So actually look at this one, right? Thank you. Okay. So the first one was right, the 0, 0, 1. Anybody gets that right? But the second one already failed. You go through this is plus 0, plus 0, plus 0. And in fact, the result is indeed 1 minus 2m over r, which means the 0, 0 component in the Eddington-Finkelstein coordinates is the same, a component is the same as before. Okay? So now we calculate the 1, 1. Is there still a question? Now we calculate the 1, 1 component according to the same scheme, but now we go with respect to d1, d1, dxm, dxn, gx, mn, and now of course we need to look at all the ones in this column and multiply them each time squared. Why squared? Well, because that's the same and this is diagonal, so only those appear. So we get a minus 2m by r minus 2m, and we get that twice, and we multiply with the 0, 0 component, which is 1 minus 2m over r, plus we get the next one, which is a 1, and yet another 1, and we multiply with the 1, 1 component, which is minus 1 over 1 minus 2m over r. Is that right? I think that's right. So let's try to get this straight. So what is this? This is 4m squared divided by r minus 2m in brackets squared. And here you have r minus 2m divided by r. It's the same thing. Minus 1 over r minus 2m, and we put an r here again. That's right, no? And then this square here goes against this factor up here. And then you get 4m squared by r minus 2m is this over r here minus r minus 2m r equals r minus 2m and is this right? 4m squared by r. Let me see whether this is right. Minus r. Can this be brought to any meaningful form?
Yes. Put an extra r.
So I do what? I divide by r. So I expand or I cancel? What do I do? By what? By times r. Aha. Okay. So this is 4m squared minus r squared by r squared minus 2mr. And now? Okay, now I start understanding r minus 2mr, and now you want the third binomial or something. Something like that, right? Who's laughing? So this is minus, if I cancel this against this, I get a minus 2m plus r by r, and that is, okay, that's what it is, right? Because 2m minus r divided by r minus 2m. I think that's approximately right. So this is minus 1 plus 2m over r. Okay, that's it. And okay, as you can see, I have serious difficulty performing these calculations. As I say.
Very strong.
Yes, okay. So there is yet nevertheless one we need to calculate. That's the 0, 1, 1. But I won't bore you with that. It works according to the same along the same lines. Only that now you have these others, tra-la-la-la-la. I won't embarrass myself even more. So the result, if you do this properly, is minus 2m by r. So that means we produced an off-diagonal element. And of course, this one is the same as the gy 1, 0, because it's symmetric. They're both this here, and all the others are unchanged. All others remain unchanged. So they're the same in the x and the y system. So what we get, result, we get Schwarzschild in Eddington-Finkel coordinates. How does it look like? It's G is the abstract tensor. That has nothing to do with the coordinate system. I take the 0, 0 component, 1 minus 2m over r dt bar tensor dt bar, because with respect to the dt bar. Now I get minus, and that's the thing, I get this mixed element. This is minus 2m over r, and this is true for the dt bar tensor dr, but also for the dr tensor dt bar. Right? I mean, this is this element on the right, upper right and lower left. Then comes the minus. So actually, they're all pluses, but because there's a minus in here, it is minus 1 plus 2m over r dr bar tensor dr bar. It continues, but what continues is the old stuff. Minus r squared of the theta bar. Well, strictly speaking, I have to call the r bar, right? So d theta bar tensor d theta bar plus sine squared theta bar d phi bar tensor d phi bar. But it's good custom to drop the bars on the r's, because really the r was not changed, okay? And the bars on the thetas, although very strictly speaking they belong there, but they're still the old coordinates like in Schwarzschild, okay? Okay, so this is the Schwarzschild metric and Eddington-Finkelstein coordinates, and that's a result that's useful. Yes?
Was it just for pedagogical reasons that you start with the Schwarzschild metric and then derived it from there, or can somebody directly with considerations get to this point?
Well, it would be bad pedagogical reasons, because the Schwarzschild chart is not a very good chart. But the point is, we start with the idea, well, we have a spherically symmetric solution. Let's start with the polar coordinates that come to mind if you want to describe a spherically symmetric solutions. In the time direction, well, let's say that goes from minus infinity to plus infinity. We allow everything, we think. Then we plug this into Einstein's equation and we get the solution in Schwarzschild coordinates. Now, this teaches us a lesson. It teaches us the lesson that whatever chart you come up with, which you think might be a good chart to cover virtually everything, the Einstein equations may report back to you, look at the solution, look at what the geodesics are doing, and if you have geodesics running to somewhere, and they do this in finite parameter time, in finite affine parameter time, especially also the time-like ones, and they don't seem to hit any boundary, but they stop because the chart ends, right? There are chances that your chart is chosen too small, although formally it's blown up to the whole plane, but that may be just an artifact. So in fact, the coordinates we thought are good coordinates by intuition, by making an ansatz, blah, 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 it turns out that just a small part of what the Einstein equations report back to you. Do you now see how important it is that we get this idea right, what's the real world and what's the chart? Because otherwise you say, if you only think in charts, this would be the most mysterious procedure to change to another chart and to insert points. I mean, it is a magical procedure to go beyond infinity. But if you think of charts, it was some very normal thing. Apparently one shows a very funny chart.
So
Yes.
also how people discovered
Yes, yes, yes. So in the beginning they took the other coordinates, and then one tried to understand what this r equals to m means, and Einstein first didn't understand because he thought the manifold ends there. He thought you only have this outer solution and the other one is another solution of another space-time, right? Because he was still thinking in charts a lot. And so with time people realized we have to study this at the level of differential geometry. And so there are many indicators why, I mean, I gave you an intuitive indicator. They run out and they come in and da. Okay, so the technical thing you do is you ask, is the space-time maximally extended? Now what is that? You look at geodesics and you see whether geodesics continue for infinite parameter. That's a complete geodesic. We had this notion of completeness. Or whether the geodesic stops because it hits a singularity. But the geodesics of Schwarzschild that went out the chart up there in the Schwarzschild coordinates, they didn't hit any singularity. And if you followed the affine parameter, which we didn't do, you would have seen it's not affine parameter infinity. You can also do this for time-like geodesics, where you then have the natural parameter, the length, the time, the proper time by which you can parameterize them. And you see they run there in finite time. It's like you have this map of Linz. And you see that your father in the morning is driving away like this. And after half an hour, he has reached this point. And then 10 hours later, he comes back. So the suspicion is that he did something here. Okay? Whereas if the chart was a different one, and you would drive in proper time parameterization, and you never arrive up there, right? You never. So you maybe you come closer and closer and closer, but no matter how much you extend your proper time for a time like geodesic, you never arrive at this boundary. Well, then there's no problem. Then you have no suspicion that there's something beyond the boundary. So this is an informal discussion of the notion of maximal extension. Yes. No, as I said, I made this fine distinction between affine parameterization, which includes the proper time, but also for null geodesics, you can have an affine parameterization, which is actually always the case if your geodesics satisfy equal 0 rather than chi times v gamma. You remember the distinction between autoparallels and so parallel and parallel transport and so on. So this is Pinocchio with the nose always being 0 or something. Okay, no, Pinocchio not lying, the non-lying Pinocchio. Okay, so also for null geodesics that makes sense. Okay, and what comes out is the affine parameterization, and that you can use. Yes.
Is there any deep meaning in having cross terms between time and space and r? Because we did the correction by, well, the correction gave us
This.
cross term.
Yes. Yeah, well, in general, you have, if you go to crazy coordinates like those ones, then the whole matrix is full of terms. Okay. If you have these cross terms, it doesn't look static anymore. It may still be stationary because none of the components depends on the new time. So d by dt bar is still a Killing vector field, a time-like Killing vector field. You might have the suspicion it's not stationary anymore, because for stationarity there's a coordinate system where this goes away, but you know that's only fake, because in another system, in the Schwarzschild coordinate, it goes away. Okay, so the first approximation to your answer to your question is no. There's no deeper meaning, it's just a different coordinate. Nevertheless, cross terms one usually discusses. Yeah. Further question? No. Okay, fine. So we have the this in the new coordinates. Okay, so we have the final bit, that's Kruskal coordinates. And I won't do this in detail because you can read it up. There are many good books that do that. But the idea is do further coordinate transformations, changes, such as to also have the outgoing null geodesics appear as straight lines now of slope +1 in the chart. And I will just draw you the resulting picture of Schwarzschild in Kruskal coordinates. Look up how they're defined. Very roughly speaking, for the Eddington-Finkelstein coordinates, at the horizon, we pulled down from infinity, we pulled down the points, you remember? Now here, you also pull some up from below, very roughly speaking. And you don't only do this at the horizon, but at the horizon you do this infinitely and something like this, right? You do it like this. And very roughly speaking, and the resulting picture of Schwarzschild in those Kruskal coordinates is, and there's a surprise, and I try not to spoil it. So in the Kruskal coordinates, the Schwarzschild space-time looks like this. It's the interior. This is the outer region. So this inside is the black hole. Well, before I should have already drawn where the black hole is in the Eddington-Finkelstein, of course, to the left from your point of view of the horizon, right? And then, of course, you think of this rotated, and you have one more dimension, and of course, this 2 dimensions suppressed. Now, this here is the outer region. And this is the black hole region, and this is the singularity. And here, now really, all light rays run, all infalling ones, go like this. Chop, and they hit the singularity. Chop, they hit the singularity. But also the outgoing ones, they go like this. This one evades the singularity. This one evades the singularity. This one is already inside the black hole. Everything that's inside the black hole invariably falls into there. Okay? But there's a surprise. So this is, we say, okay, this is other coordinates, so what before was there, it's now here like there, and okay, the singularity is space-like because it was before. You see, before, the singularity was here, but then the cone stood like there, so the singularity was space-like. You see what I mean? So that's fine, that looks good. The Eddington-Finkelstein that we had before, which corresponds to this in Kruskal coordinates, is still not the maximal extension. It turns out there is a second outer region we didn't see before. It's the outer region 2, whereas this was the outer region 1, which was the only one that was visible in Schwarzschild and the only one visible in Eddington-Finkelstein. But all of a sudden, that was not the maximal extension. There is another outer region, and there is, and now you will rightfully be shocked, you see that these guys, they actually came from here. And these guys, they actually came from here. Oh, that's a terrible situation, because this is a singularity. All hell breaks loose at the singularity. And from there, stuff comes and moves here. That means an observer going about his business here, right? So an observer going about his business right here will receive information from the singularity. We should be able to see singularities if this really is physical. But as a solution of Einstein's equation, it's the maximal one. And so this is called a white hole. It's the black hole. Things can only fall in but never come out because of the time orientation. From the white hole, stuff can only come out and not fall in. You see this here because light always runs at this here, and if the other light then runs here like that, then you see that massive stuff could also at most run out. You see? Aha. So there's this whole second part to this. And now you can start asking questions like, what on earth happens here? And you can study, so in this Eddington-Finkelstein coordinates, so this is a new coordinate T double bar that goes in this direction, you can ask what actually happens. I draw the diagram new, because otherwise it's too much in one diagram. What happens, so chuck, 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 1, 2, chuck, 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 ha, ha, ha. So again, this is Schwarzschild, maximally extended, but that's the end of the game. Okay. Now you can ask, what happens if I look at spatial sections that evolve like this? There's this one, and this one. So if we look at this one here, this is part of the outer region which we believed to understand, right? And so on. Now look at this one. This is this outer region which we believe to understand. The point is what happens, so these are like two universes which have no causal contact to each other, because nobody in here can signal anything to someone here. Can you see that? Because light always runs like this. You would have to signal faster than the speed of light in order to send a signal from in here to here. Agree? That means nobody here can signal anything to anybody here, and nobody here can signal anything to anybody here if you look at this level. But remember that we suppressed 2 dimensions. So at every point here, there is still a 2-sphere attached of various size. It depends, you need to look at the line element to study that. And it turns out that as t progresses, and you look at these green guys here, can you see the green on green? Or, yeah? There is a topology change of the spatial sections. Topology change of the spatial sections in green. Okay? And so if we look at this one here, at t equals 0, you can read this, yes? I think I feel uncomfortable. I use another color. So let's look at this one here, this whole one. At t equals 0, that actually looks as follows, the spatial bit, right? it looks like a throat. I suppressed one dimension, so this is a two-dimensional spatial, so I suppressed one spatial dimension, suppressed, and it's supposed what in this picture is just this here. Okay, so this one here corresponds to this upper half, and this one here corresponds to the lower half. But if you're here before, things happen. So let me draw this here. At this time, it looks like this. I do it now even one dimension more reduced, but this is the throat. Okay? Now, if you move in time down here, all of a sudden, this will be disconnected. It will look like this. So this part is this guy, and that part is that guy. So they're two separate outer regions, right? But here they come closer and closer together. Hang on a second. That's so no. Here they're the farthest apart. They're the farthest apart. So from here they now join. Looks like this. Then they move apart. Then they join again. And then they do that again. And that is what, so that's the evolution here. If you proceed in this T bar bar. Okay? Crazy stuff is happening there. Well, this requires careful analysis of the full line element of Kruskal, which I didn't write down. I only wrote down the diagram that suppresses this. Okay? So then you can start speculating. So this is called an Einstein-Rosen bridge. And you can start speculating whether you may provide additional global conditions for how this goes, and then you have here the throat. And if so, we had the throat before, now it's connected here like this. You could provide this by hand, something like this you would then call a wormhole. That would mean you start for Schwarzschild with a different topology from the start. And stuff like that. So you can imagine crazy stuff that solves the Einstein equations, and these are all possible solutions if you make the right provisions. Okay, anyway, this is the maximally extended Schwarzschild, if you say let's go in all directions. Now, that looks rather crazy because this white hole thing is totally nuts. And in fact, one has the idea to say that should be physically excluded because the theory becomes highly non-predictive because everything would come from a singularity, but at the singularity the theory breaks down. Whatever originates here, you don't know how to write down initial conditions, whatever, you think that quantum theory takes over, you would have a fully non-predictive theory if this was really realized like that. So what one really believes is that, for instance, if you have, so this is Schwarzschild interpreted as a vacuum solution. So there's no matter producing the Schwarzschild, it's just a vacuum solution. And as Nico Giolini explained, that makes perfect sense. We have this mass m in there, but that's the ADM mass of the space-time and so on. Okay, you can consider it a pure vacuum solution. However, if you don't consider it a pure vacuum solution, then you might think that you have some matter. So I think again in the original Schwarzschild coordinates, you have some matter falling in, lots of matter. And under their own gravitation, they fall together until they're inside. All the matter is in. So this is a picture in Schwarzschild time, T, until at some point a horizon forms because so much matter is in here and it's so dense that it's inside its own Schwarzschild horizon, and then you have a singularity here in the original Schwarzschild coordinates. Well, that's already the picture where you rotate it, where you have this, so you could think of half the picture or something like this. This would be more like a realistic picture, and then you don't have this white hole bit. Okay. However, what do I really mean by this? And is there an even better way to understand? Oh, I'm sorry. I drew the wrong picture. Ha. So this, I am sorry. I already drew. Okay. I already drew. It's not true. Okay. It's not true that this is the picture in Kruskal coordinates. I'm sorry. This is already the so-called Penrose diagram of the same, and the Penrose diagram we'll do in the next lecture. I am sorry, but the point is why I drew this is because the actual Kruskal, I'm sorry, that's very silly, it was very silly of me. So it's all true I said, but I drew the wrong picture. So the Kruskal picture looks like this. There the singularity, so there is here a hyperbola, and the singularity lies here. And so that's really the Kruskal coordinates, and the singularity lies here. And this extends everywhere, right? So this extends in all directions to infinity. Not the part that I shade here. The part I shade is not part of the picture. So this extends to infinity in all directions. The part I'm shading here does not belong to the picture, but everything that's not shaded is Kruskal. And indeed, geodesics, null geodesics, you see why I confused this. And the null geodesics here, they all run like this. They hit here, you call this the black hole, you call this the white hole, right? You have other null geodesics running like here, they come from infinity and they run like there. Stuff like this. This is the horizon of the black hole seen from here. This is the horizon of the black hole seen from here. The only difference is that this really extends to everywhere and extends here to everywhere. And the only difference to the Penrose diagram is that here one did an additional trick. One took the null directions and one compactified them in this way, in order to bring the whole space-time, so only what is inside here is a picture of the space-time, okay, in order to not have the problem to say, well, what really happens here at infinity, because it's so difficult to think about it, you compactify along the null coordinates, and that will be the topic of the next lecture, in order to compactify this picture to this. And then you have a Penrose diagram. In this Penrose diagram, but you see it's virtually the same, apart from this being compactified. So I please apologize that I drew this and I said it's in the Kruskal coordinates. Again, this is not in Kruskal coordinates, this is in conformally rescaled coordinates, whereas this is the picture in the Kruskal coordinates. That's very similar, and we'll discuss the construction of such Penrose diagrams where you can really fit an entire space-time on a small sheet of paper. Well, if you suppress two coordinates and stuff like this, okay? And here, because the cones always everywhere stand up like this, you can very easily see which regions are connected, causally connected to which regions and which are not. From where to where you can send signals. Okay, so that was it about the black holes. The Schwarzschild black hole, there is a charged black hole that's called Reissner-Nordström solution. It's a bit more complicated. There is a rotating and charged black hole that's called the Kerr solution. So rotating black hole is no longer spherically symmetric in space, but in space only cylindrically symmetric. Of course it rotates. There's a distinguished direction in space and so on. And so there are many different black holes. However, there's much to be said about black holes. For instance, black holes don't have hair. So if they form, and one believes that the Kerr black hole is the most general form, it can rotate. A black hole that only has mass, one charge, and one angular momentum. You can say, but shouldn't there be black holes that have a little bump here and a little bump there, so black holes that are not like spherical or cylindrical if they're rotating? Well, the answer is no, right? So it's very general because with time, all the asymmetries would be radiated away by gravitational radiation. Okay, so black holes are really a very special class. Of course, you can, there are abstract definitions for horizons and the different types of horizons and so on. So all of that, if you want to learn that, you go to literature and read a book on black holes. But these are the basic ideas that we displayed here, and from there you need to take it yourself. Thank you very much. Yes.
May I ask a question?
Yes.
So I have the feeling that if one reaches now this horizon between outer region and the black hole, yeah,
Yes.
some strongly non-linear behavior in time is going on. We did some rescaling, some coordinate transformations.
Yes.
Can one now interpret this if an observer, yeah, goes into the black hole and how his clock arising this horizon, does the clock going faster? Is my impression.
From
that it's
whose
going
point of view?
in my lifetime, would I reach the horizon? Is my
Yes.
recognition slowed down, or is it does it go faster? So,
Yes.
So this is, I do not even know the non-linearity now, in which direction the scaling, the non-linearity is going.
Yes, yes. So the point is, somebody falling into the black hole, for somebody out here, it appears that that person will approach more and more and more and more the horizon, but you can discuss from this picture that if somebody, can we have some? So you can imagine from this picture, somebody falls into this black hole as a massive observer, and there's a massive observer, say, out here, looking, observer's always massive, then you will receive information by this guy sending, I'm still alive, I'm still alive, I'm still alive, and so on. Well, the point is actually the massive one in this Penrose diagram, we'll see this later, will always arrive here as a geodesic. So this guy will receive information from this guy till the end of his own lifetime, which may be infinity, which here is infinity. You will live infinitely long here as an observer. This guy's clock here goes like 1 hour, 2 hours, 3 hours, boop, I'm in the black hole 4 hours, 5 hours, and so on. But the guy out here will wait for millions of years, and he will only see that the guy comes closer and closer and closer. In his time, you wait 1 million years and the other guy hasn't fallen in, although on his own clock, he fell in after an hour. Sounds very strange, but that's his clock and that's his clock. Okay, so let's reconvene at 1/4 past.